a couple examples from this chapter, kind of using the equations and making sure we're all on the same page. A couple things, you really want to draw a picture so you can have an idea of what's going on. So let's look at this problem. I know word problems tend to scare people, but really if you go through sentence by sentence and break it down, we'll definitely get through this, and they're not as bad as what you remember. So you have a football quarterback that runs 15 meters. So let's say that this quarterback runs an initial, from here, runs 15 meters and going straight down the field in 2.5 seconds. And then he then gets hit and is pushed 3 meters backward. So then he goes this way for 3 meters, and it takes 1.75 seconds to get pushed back that far. He breaks the tackle and then runs forward another 21 meters. So then he turns around and he starts going this way. "21 meters," and he takes 5.2 seconds to run that time. And so it doesn't really tell us if he's getting faster or slower. We know that for him to start running, he's going to have to get faster, and he's going to have to decelerate when he gets hit and so forth. So we know that's happening, but what happens is we want to look at this question here. It says calculate his average velocity. Now I haven't given you an equation for average velocity, but if we look at this equation here, x is equal to v naught t plus 1/2 a t squared. And if we look at this, we don't really know what's going on with the acceleration, if he's getting faster, slower, so forth. So we're just going to let that term go to 0, and we're going to look at overall, if he is not getting faster or slower, what is his average acceleration? So if we look at this, that means velocity is equal to x over t, or I can say velocity is equal to delta x over delta t. Now, I want to put a red flag here, okay? Put a red flag right here. This is a dangerous equation because it doesn't always work this way. Okay? The first equation, x equals v initial t plus 1/2 at squared, is always true, but this equation here is only true if the acceleration is 0. Okay, so remember in the previous videos I've talked about going through and making sure you really work from those 3 basic equations. Again, you will see this equation, velocity equals delta x over delta t, on Chegg. You'll see it on tutorials. You'll see it in the textbook. But it's only true if acceleration equals 0. So it's not valid all the time. This equation is valid all the time. So really kind of don't set yourself up for failure. Go back to the original equations and work from there. So I'll color code this. It asks calculate the average velocity for each of the 3 intervals, and then for the entire motion. So let's look at the black interval here. So I've already derived the equation, so I don't need to derive it for every step. So if you're working on a problem that has multiple steps for an exam or something, if you derive the equation once, you don't need to look at it again. So my change in displacement is 15 meters over 2.5 seconds. I plug that in, and I'm going to get a velocity equal to 6 meters per second. Okay? So that's my velocity in the black area. And kept units and so forth. You can see where the meters per second is. If you notice, I'm not really a stickler on sig figs. I prefer not a calculator answer, but you're going to see later on this semester where rounding can really be a problem and cause error, especially on the homework package or any online homework. If you round before you get to the end, it can cause problems with your answer. So let's go to this blue section here. Velocity is equal to delta x over delta t. But we're going backwards. So this is going to be a key thing here. This is minus 3 meters divided by 1.75 seconds. So this right here is because we're going backward. Okay? So that gives us a velocity equal to a negative 1.71 meters per second. Doesn't mean I'm going slower, just means this right here means I'm going to the left. So no big deal there. Now I want to do the same thing for the green. And this is equal to 21 meters over 5.2 seconds. I'm going forward, so everything is going to be positive. Time is always positive, by the way. We're always moving forward. And I'm going to get a velocity here of 4.04 meters per second. Okay. So hopefully this makes sense with the individual ones. Now, what's going to be interesting is how we handle this last part right here. I want to do it over the total point. I want to go from here to here. What is my total velocity in this area? So my velocity is going to equal the change in x over change in t. From beginning to end, this is my change in x. Okay, so I go forward 15 meters, and then I go backward 3 meters, and then I go forward an additional 21 meters. So if you're looking at this, that means I have a total distance traveled of 33 meters, total displacement. So if I'm looking at displacement versus distance, your Fitbit does this. So for example, your Fitbit would measure 15 plus 3 plus 21, or 39 meters that you've walked. Your total displacement works at a vector, and that's from beginning to end, the shortest path. Okay, so we're taking our shortest path from beginning to end. So from point A to point B, and that means we went a total of 33 meters. Well, how long did it take us to get from point A to point B? So that's going to be 2.5 seconds plus 1.75 seconds plus 5.2 seconds, or that is going to be a total of 9.45 seconds, or my velocity is going to equal 3.49 meters per second as my average velocity. Okay, so now let's look at this next problem here. So a fireworks shell is accelerated from rest to a velocity of 65 meters per second over a distance of 0.25 meters. How long did the acceleration last? And calculate the acceleration. So let's look at a couple things here that we want to kind of pinpoint. So let's look at what we know and what we can pick out from this problem. A fireworks shell is accelerated, so we know we have some acceleration from rest. What does that mean? It means my v initial is 0, so we'll write that here, to a velocity of 65 meters. So this will mean my v final over a distance of 0.25 meters. So the questions that are asking, how long is time? And then calculate the acceleration A. So when we're looking at this, we want to go through and look at the... Apologize, my dog wanted to join class. So if we go back and we want to look at this. So one thing that you want to kind of remember or think about is you can actually solve B before A. So we kind of want to look at some things. We have our three equations. I already have the three equations here. And I'm trying to find time. So if I'm trying to find time, this equation here really isn't going to be a great equation. Okay, so I want to look at the other two equations first before I would come back and look at that equation potentially. Okay, keep in mind, we may come back to this, but for right now, for time, that's a frowny face equation. So if we look at the other two equations, I have my x, so that's good. I have my v initial. That's good. I'm trying to find time. I do not have my acceleration. I'm trying to find time. So I have two unknowns here. And let's look at the next equation. I know v final. I know v initial. I do not know my acceleration. And I'm trying to find time, so I still have two unknowns. So I could use these two equations here, isolate and substitute, and do some algebra and solve for A and solve for T. But let's come back to this equation right here. So let's go back and let's look at this equation. V final squared equals V initial squared plus 2AX. I would prefer not to have to isolate and substitute. I would prefer to plug and chug. So I know my V final, I know my V initial, I know my X, and I only have one unknown here as my acceleration. So I have two options. I can isolate and substitute with the equations that are with red hash marks or red asterisks, or I could solve for A in the green equation and then use either of the equations up there with the red asterisk and then solve for time. So I think that's what I'm going to do. Either way is correct. What is awesome about physics is there are multiple ways to do the same problems, but this is one of the ways to go through and do this. So also, you can either plug the numbers in now or you can wait till later. I'm going to go ahead and plug the numbers in. I have 65 meters per second squared is equal to 0 squared plus 2 times A times 0.25 meters. So when I do this, I get 65 squared. And if I make a calculation mistake, please let me know. It's a whole lot easier face-to-face for people to tell me I messed up, but please email me and let me know I've messed up. So 65 meters per second squared is 4,225 meters squared per second squared equals 0.5 meters times A. Now, for me to get the 0.5 over, I need to divide everything by 0.5 meters. So divide that by 0.5, and I get an acceleration equal to 8,450 meters per second squared, which seems like a ridiculous amount of acceleration, but you're only doing this over about 25 centimeters, and you're going from 0 to 65 meters per second. So it's crazy. Now, little side notes, as I'm grading your exams and so forth, if you could circle your answers, that will help me find it. Now, I can take this A and put up to either one of these equations. It doesn't matter which one you choose. The one on the right has less squares, so that's probably the one I'm going to choose. But it doesn't matter which one you choose, you should get the same answer. So if I do this, now I can plug and chug numbers in again. So I have 65 meters per second is equal to 0 plus 8,450 meters per second squared times time. Divide both sides by the acceleration. Okay. And I get a time equal to 0.0077. Now we know the seconds units are going to be seconds, but let's make sure. Let's bring this down and just make sure we're good with this. So I have meters per second over meters per second squared. Remember, you need to invert the denominator, so I get meters per second times second squared over meters. The meters cancel out, one of the seconds cancel out, and I'm good to go with seconds. So my total time is 0.0077 seconds. My acceleration is 8,450 meters per second squared. Again, I know I solved for B first, but homework doesn't know that which one you solve for first. You want to choose the easier math. Again, you could solve for time first, but the math will be a little bit more complicated. So hopefully you can go through and see these examples. As you work through the problem, choose the equations that would best help you solve the equation. Write down what you know, and then look at the 3 equations and go from there, and start working and solving for what you need and what you do not have.